Okay, so good evening, good afternoon, good morning, everybody, wherever you might be. Today I have a pleasure to welcome a new postdoc to IMPAN, ANDREAS KRAFT. And he just arrived at IMPAN yesterday, so he immediately started his work by giving a talk, which we very much appreciate. And you see, we'll have a commutator question here, is formality commuting with reduction. First steps towards this problem. Andreas, the Zoom is yours, take it away.
Thank you for the introduction and for the opportunity to give a talk here. And yes, so I want to give you some ideas of the first steps towards the possible compatibility between the formalities in information quantization and the phase-space reduction. And this talk is based on my PhD project, which I did in Salerno in Italy with Chiara Esposito, and work together with Jonas Schnitzer. So let me give you the basic ideas of the setting we're in. We are interested in formal deformation quantization. And there on the classical side, you are interested in Poisson manifolds. So the smooth manifold with okay, it doesn't work. So it's a bivector field. What am I doing wrong?
This is text time, right?
I want to write. I'm sorry, I tried to use this writing tablet, but I'm too stupid, it seems. So
yeah, it works. We can see you writing.
A bivector field, so in the tangent bundle, and you want that the bracket of pi with itself, so the Scouten bracket should be 0. This is a Poisson bivector field. And then you have the smooth complex valued functions as observable algebra. We have the pointwise product on these functions, and the Poisson bivector field induces the Poisson bracket on the functions by this formula here. So you take two functions, the Theorem differential, you can insert it in this bivector field, and this gives the Poisson bracket. So it's anti-symmetric, it satisfies the Leibniz rule in each argument, and since pi commutes with itself, it satisfies the Jacobi identity. And in informal deformation quantization, you want then the description of the quantum system to be a formal deformation of this classical data. So you look for star products, and the star product is an associative product on the formal power series of smooth functions. So this h bar here is just a formal parameter. And you want the star product to deform the classical data. So the star product of two functions should be in 0th order of h bar, just the pointwise product, plus some higher perturbations. And you want that the commutator of two functions with respect to the star product is in the 1st order of h bar, Poisson bracket, and again, plus some perturbations. So here in the commutator, there can be no 0th order, because in the 0th order, the star product is just the commutative pointwise product. And okay, you want some other properties, so you want the star product to be bidifferential in each argument, in each order of h bar, and you want that the constant function 1 is still a unit. So 1 star f is just f, and the same for the right-hand side. Okay, and so deformation quantization is basically about the existence and the classification of these star products. So do they exist for every Poisson manifold? How many different do exist? And for symplectic manifolds, so when this Poisson bivector field here is non-degenerate, there is, for example, the Fedosov construction, which is pretty explicit. But for general Poisson manifolds, this is much more complicated. And well, it was solved by the formality theorem of Kontsevich. And Kontsevich proved that there exists an L-infinity quasi-isomorphism from the vector fields to the Pulley differential operators. And this L-infinity quasi-isomorphism induces then at the level of Maurer-Cartan elements this correspondence between Poisson structure and star product. So I will give you more details later. I just want to say that the formality part of the title is this quantization error. So next part of the title is this reduction. So here we will always consider the classical Marsden-Weinstein reduction, which is the nicest case you can think of. So assume that we have a Lie group action on the manifold from the left, and that it acts by Poisson diffeomorphisms, so that the Poisson vector field here is invariant under the group action. Then you have an induced action of the Lie algebra of the Lie group by these fundamental vector fields. So this psi m here is called fundamental vector field. And in our sign convention, this is now a right action. So this map here is an anti-homomorphism of Lie algebras. And well, since the Poisson vector field is invariant under the group action, these are Poisson vector fields. So you have derivative of the fundamental vector field.
Can you speak a bit
of the
louder?
Poisson bracket is 0. So these are Poisson vector fields, and you want even a bit more. You want that they are not only Poisson vector fields, but Hamiltonian vector fields. And the Hamiltonian function you call momentum map. So this is a linear map from the Lie algebra to the smooth functions. And you want that the Hamiltonian vector field of J of psi, which is defined by this insertion here, is just the fundamental vector field. So in other words, this is just the Poisson bracket on the right-hand side with the momentum map. And you want this momentum map to be equivariant, so that it's a morphism of Lie algebra. So it should map the Lie bracket to the Poisson bracket here. Okay, so this is the momentum map, and you can interpret this momentum map as a map from G to the smooth functions, or dually as a smooth map from the manifold to the dual of the Lie algebra. And then if you assume that 0 in G star is a value and regular value, then you get that the pre-image here is a closed embedded submanifold of M. We call it regular constraint surface. And this equivariance property here implies, so this equivariance implies that the group action restricts to C. So summarizing, we have this group action on a Poisson manifold with momentum map. We have the regular constraint surface here with induced group action. And then the Marsden-Weinstein induction says that if the induced action on C is proper and free, then this quotient here is a smooth manifold, and it's indeed a Poisson manifold. So you get here an induced Poisson vector field. So this is the classical setting, and now we can do the quantization part. So downstairs we have just the Poisson manifold. So on the quantization side, we would expect just a star product on the reduced manifold. And upstairs we have more data. We have the Poisson structure and the momentum map. So on the quantum side, you would expect some invariant star product with some quantum momentum map. And this pair is also called equivariant star product. And the nice thing is that there's a reduction scheme for such equivariant star products due to Borderman, Herbig, and Waldman. So which gives out of such an equivariant star product on reduced manifold. And what we would like to understand is now if deformation quantization and phase-space reduction commute in some sense. So the first thing we have to do is to understand this arrow here a bit better, because this is not just the conservative formality, but you have to modify it a bit so that it includes the momentum map and the group action. So this is not completely obvious to get this arrow. And well, if you had it, you could try to do some brute force computations. So you could take some Poisson structure with momentum map, quantize it, reduce it, and try to show that it's the same as if you go the other way around. But this is pretty hard because the formality is very complicated. So what we would like to do is to understand this diagram at a more general level, so in the sense of L-infinity morphisms. So I said this arrow here comes from conservative formality. This arrow upstairs is some kind of modified conservative formality, also called equivariant formality. And well, what we want to do is to describe these reductions here in terms of L-infinity morphisms. And then in a second step, you could then try to investigate if this diagram of infinity morphisms commutes. Okay, but today is just about describing this in terms of infinity morphisms.
I have a question.
Yeah.
What if we replace 0 by some other regular value for this moment path?
There is some shifting trick with quadrant orbits that you can get back to 0. So this is not a strong assumption.
Yes, but what is happening on this DRST side? If we change.
So if you take here a different value as 0, then you don't divide here by the whole group, but just by the stabilizer group of this value. Yeah. And this works also on the BRST side.
But what happens on this contrast side?
So this works also with this subgroup reduction. Okay, so now the outline of the talk. At first, I have to recall some basic stuff about Markov-Cartan elements and infinity algebras, infinity morphisms, and the twisting procedure here. Then I want to describe the conservative formality in a bit more detail and its globalization procedure by Dolgushev. Then the third point is this equivalent formality, so this formality that is compatible with momentum maps and the group action. And then the reduction morphisms for vector fields and differential operators. So let's start with the basic definition of a differential graded Lie algebra, a DGLA. This is just some set graded vector space with a graded Lie bracket. So it's of degree 0, it's graded anti-symmetric and satisfies graded Jacobi identity. And you want a differential, so linear map of degree 1. It squares to 0 and it satisfies some Leibniz rule here. And then you have in DGLAs some special elements called Markov-Cartan elements. And they are just some elements of degree 1 that satisfy this Markov-Cartan equation here. And well, the nice thing is that if you have such a Markov-Cartan element, you can add the Lie bracket with this element to the differential. And the Markov-Cartan equation implies that this is again a differential. So it satisfies the Leibniz rule because this is an inner derivation, and it squares to 0 just because of this Markov-Cartan equation.
But I'm confused. Why do you use the same letter pi, which used to stand for Poisson structure, not for Markov-Cartan?
Because Poisson structures are special examples of Markov-Cartan elements.
Okay,
so this will be the first example later.
Okay, thank you.
Yeah. Okay, so for the conservative formality, this would be sufficient. There you only need like DGLAs. But for this equivariant formality with the group actions, we need something a bit more general. So we need curved DGLAs. So we have a special element of degree 2, which is called curvature. And now the differential is no longer really a differential, so it doesn't square to 0, but the square is the bracket with this curvature. And you want the curvature to be closed. And then you can adapt the notion of Markov-Cartan elements to this curved setting. So we just adhere the curvature in the Markov-Cartan equation. And well, then you can twist curved DGLAs with general elements of degree 1. So if you have a curved DGLA, pi is just a general element of degree 1, and you consider this one, then this will induce the curved DGLA structure where the curvature is here at the left-hand side. So in particular, if you twist the curved DGLA with a curved Markov-Cartan element, you get a flat DGLA. Okay, so this is the general definitions of Markov-Cartan elements and DGLAs. And well, let me now show you the examples why this makes sense for deformation quantization. And here is the example of the Poisson bracket. So consider as DGLA the Pulley vector fields. So these are just vector fields with this degree shift by 1. Then a Markov-Cartan element is an element of degree 1, which is because of this degree shift by vector field. And the Markov-Cartan equation is just that the bracket of pi with itself is 0, because the differential is 0 in our DGLA. So Poisson bivector fields are Markov-Cartan elements in the Pulley vector fields. Now to the case of group actions and momentum maps, there is a curved DGLA called equivariant Pulley vector fields. And this is due to Richard Nest and Boris Ziegen. And the underlying vector space is now the Pulley vector fields tensored with the symmetric algebra of G star, and then the invariants, where you take here the coadjoint action on G star, and G star is concentrated in degree 2. The Lie bracket here is just the Schouten bracket trivially extended to this tensor product. The differential is again 0, but now you include here some curvature term. So choose some basis of the Lie algebra with dual basis, and then the curvature is just given by the fundamental vector fields tensored with the dual basis elements. So, well, to show that this is a curve DGLA, we have to show that the curvature is closed, but this is clear because the differential is 0. And we have to show that the square of the differential is the bracket with the curvature. But this is also true in this case because the curvature is central, so the bracket with lambda vanishes. So this is a curve DGLA. Let's look at its curved Maurer-Cartan elements.
I have another question. What if we replace this Cartan model for equivariant things by, let's say, Weil model?
So here, some
Is this
wedge
construction
options
dependent on the choice of the model of DG? Right model or DG?
I don't know. So the way this DGLA is constructed is just that Maurer-Cartan elements are Poisson structures with momentum maps. So if you would change it, you would get different momentum maps probably. So you know what I mean?
Yes, of course. So this is called the Cartan model.
Kind of.
Yeah. Or something.
Yeah, I will later have something else which is also Cartan model. Maybe this makes it a bit more clear. So the definition of this curve DGLA is just in such a way that Maurer-Cartan elements are pairs of Poisson structure and momentum maps. So this is the main motivation to define it like this. And well, the proof is pretty easy. So just take an element capital pi of degree 1. Then the Maurer-Cartan equation is of this form. And then you can decompose this Maurer-Cartan element into 2 terms. So what kind of elements can have degree 1 in this equivariant DGLA? So you can have no G star component and degree 1 in the Pulley vector fields. So this is an invariant bivector field, which will give later the Poisson structure. Or you can have like 1 G star component, which is of degree 2, and then a -1 degree component here, which is just a function. So this is just a linear map from G to the functions, Lie algebra to the functions, like the momentum map will be. And so the Maurer-Cartan equation written with this decomposition here, we get these 3 terms because the bracket of J with itself vanishes, so we get just the bracket of pi with itself and bracket of J of pi. And then this implies that this here vanishes, so pi is an invariant Poisson structure, and the other 2 have to cancel, and this means just that J is an equivariant momentum map for pi. So this is just the way it was constructed. So these are the 2 DGLAs for the classical setting, Pulley vector fields and equivariant Pulley vector fields. And for the quantum setting, we can do the same, but now it's just differential operators instead of vector fields. So the underlying vector space is just here the differentiable Hochschild cochains. There is the Hochschild differential, the bracket is the Gerstenhaber bracket here. And when we choose the sign convention, that the Hochschild differential is just the bracket with the pointwise product. And then you can look at formal Maurer-Cartan elements. So Maurer-Cartan elements that start here with h bar degree at least 1. And the curve now, so the Maurer-Cartan equation is just this one here. Since the differential is inner, you can rewrite it like this. And then you know that the Gerstenhaber bracket just encodes the associativity. So this means just that mu plus h bar m star is an associative multiplication. You have in 0th order, it's just the pointwise product. And then you can show that in the 1st order of h bar, there is some Poisson structure included. So this is indeed a star product. So formal Mauritian elements in here are one corresponds to star products. And some remark. So here we consider just formal Mauritian elements, so starting with H bar order at least 1. And the point is that in this case, the formal power series induce a complete descending filtration just by these H bar orders. And then there's a general statement that if you have a DGLA with a complete descending filtration, then you can define a kind of gauge action on Mauritian elements in the first order of the filtration. And then you denote the equivalence classes by def for deformations. So this gauge action is interesting, and we want to have like the same for Poisson structures. So we can do the same. We can consider like formal power series of Pulley vector fields, and then formal Mauritian elements in there, and they are just formal Poisson structures. Okay, so this is the DGLA for star products. Now we need the same with the group action included. And this is similar to the vector field case, just that we use the differential operators here instead of the vector fields. Again, invariance and G star and TP2. And well, the bracket and the differential are again just gas number bracket and Hochschild differential trivially extended to this tensor product. And the curvature is again given by the fundamental vector fields, tensored with the dual basis. And now, because we're in the case of formal power series, it turns out to be useful to rescale it by H bar squared. And then you get the same statement as for vector fields. So the curved formal Mauritian elements in here are equivalent again to such pairs. We can decompose it again into some H bar M star, which is a bidifferential operator, and in some H bar H, which is a linear map from the Lie algebra to the formal power series of functions. And the curved Mauritian equation simply implies that this here will be a star product, an invariant star product, and that H will be a quantum momentum map. And so quantum momentum map means that we have these two conditions. So the first one means that the classical action by the fundamental vector fields is the same as the quantum action, which is given by 1 over H bar times the star commutator with the quantum momentum map. And you want that this H is again equivariant, so it should map the Lie bracket to 1 over H bar, the commutator. And yeah, the pair star H bar is called equivariant star product. So this is the structure which you can reduce to reducing it. And I mean, these two identities make total sense because they are just the compatibilities we had for the classical setting, just that we write now 1 over H bar star commutator instead of the Poisson bracket. So in the classical setting, we had just J of the Lie bracket should be the Poisson bracket of J of psi, J of eta. And now instead of the Poisson bracket, we have just now 1 over H bar, the commutator. Okay, so now we have like 4 DGLAs whose Mauritian elements are just the structures we are interested in from our diagram in the introduction. And now we have to generalize all the definitions a bit more, because I told you that the quantization arrow is like the conserved formality, so this is an L infinity morphism. So I need to introduce some definitions for this. And the first one is the definition of an L infinity algebra. And one possible definition for this is that you say the curved L infinity algebra structure on some vector space is a degree 1 codifferential on this co-algebra. So this is the co-free, co-nilpotent, co-commutative co-algebra co-generated by L shifted by 1. And well, it's just here the symmetric tensors with the shuffle co-product. And then, since this co-algebra is co-free and co-generated by L, this co-differential here is determined by its projection to L, so by such a sequence of maps. And they are called structure maps or Taylor coefficients of the co-differential. And well, the fact that it's co-differential, so that it squares to 0, leads then to such a series of equations for these structure maps. So here the x's are just elements in L. sigma is a shuffle permutation. So this means that sigma of 1 is less than sigma of 2 is less than less than sigma of k, and the same for this here. So just that they are ordered somehow. And this epsilon of sigma is some sign corresponding to this permutation. And well, the way to think of these structure maps is just this Q10. This is just an element in L of degree 2. So this is kind of the curvature. The next one, the Q11, is kind of your differential, and then the next one is the bracket, and then you have some kind of higher brackets.
And this symbol means what? This one?
This means that it's a map. So this 0 means that it goes from the symmetric degree 0 of L to L by 2. So here's 1 degree shift missing. And this is just K. So this Q10 is just if you want an element of L. So you know what I mean?
I was asking about this thing, like which looks like the sign of alternative. What the?
Sorry, which?
This one.
This is the shuffle. Yeah, this is symmetric product in the symmetric tensor algebra.
Okay.
Sorry. Okay. So this way of thinking is also like the way you include DGLAs in the setting of infinity algebras. So you said Q10 is minus the curvature, Q11 is minus the differential, the next one is the Lie bracket up to a sign and no higher brackets. And then if you look at these conditions, then for n equals 0, this is indeed just that the curvature is closed. For n equal 1, this means that the differential is squared is the bracket with the curvature. The next one is the Leibniz rule, and then you get Jacobi identity. So all the identities you want for curved DGLAs. So this is the generalization of DGLAs. Now the generalization of the morphisms. So an infinity morphism between two infinity algebras, I will denote it by this zigzag arrow here to distinguish it from DGLA morphisms, or just linear maps, or something else. So this is just a morphism of graded coalgebras here that commutes with the codifferentials. And well, again, because this here is co-free, this morphism is again determined by its projection to A prime. So by a sequence of maps. So we have again some structure maps. And well, the fact that F commutes with the codifferentials leads to some other compatibilities. So for example, if L and L prime are both flat, then the lowest order compatibility is just this one. If you have some additional curvature, you would get here some additional term. So you would get here plus F1, 2, and then the curvature times the element you started with. Okay, so well, and if L and L prime are both just DGLAs, then of course DGLA morphisms are an infinity morphism with just one structure map with just the 1, 1 component. And well, for the flat setting, this fact here that the first structure map is a chain map is very useful for the following. So because you can define, you call F and L infinity quasi-isomorphism in the flat setting if this first structure map here is a quasi-isomorphism of cochain complexes. And this class of L infinity quasi-isomorphisms has many nice properties. So one is, for example, that it admits quasi-inverses. So the statement is that if you have an L infinity quasi-isomorphism from L to A prime, then there exists a morphism in the other direction that induces in cohomology the inverse isomorphism. Okay, so this is one thing. And the other thing is that L-infinity morphisms are very nicely compatible with Maurer-Gatan elements. So I wrote this proposition just for DGLAs, but this also works for L-infinity algebras. So you can generalize the notion of Maurer-Gatan elements to L-infinity algebras, and you can also generalize the equivalence relation to L-infinity algebras. But well, DGLAs are for us sufficient. So let's assume that we have an L-infinity morphism between two DGLAs and some Maurer-Gatan element in the first order of the filtration. Then the claim is that this element here is a Maurer-Gatan element in G prime. And so this is the reason why we need this complete filtration. So for example, if our filtration is just found by formal power by H bar degrees in the formal power series, then each F1n will have H bar degree at least n. So this series is well defined as a formal power series. Without the filtration, it would not be clear that this series is well defined.
May I ask a question about this theorem?
Mm-hmm.
So it is a classical theorem that L-infinity is quasi-isomorphism between L-infinity algebras can be inverted, L-infinity inverted, okay, provided quasi-isomorphism.
Yeah.
Okay, so what is new in this?
No, this is
this Q.
No, this is the classical theorem. This is the classical statement.
Okay, because there are no credits, so I don't know.
Okay, I don't know.
About the original.
I don't know who did it first, but this is just. So in this section, all the stuff is old. So I just reintroduced new things.
Okay.
Okay, so F maps Maurer-Gatan elements to Maurer-Gatan elements, and it's even compatible with the equivalence classes. So it maps equivalent Maurer-Gatan elements to equivalent ones. And again, if we have a quasi-isomorphism that is compatible with the filtration, then this map is even a bijection. So this will be the reason why the conservative formality classifies star products. Okay, so one last thing in this section is the twisting procedure. So assume that we have some infinity morphism between two DGLAs and some element here of degree 1, again with the filtration. Then I told you before that we can twist the DGLA with this pi, and that we then get here this curvature, so it's curved DGLA. You can do the same in the image. You can twist it with this FMC of pi from the last slide and get again some curved DGLA. And the statement is just that there also exists a twisted morphism between those. And you can give a formula for the structure maps of this twisted morphism. So the x's are just elements in G, and then the structure map of the twisted morphism is just the structure maps of the usual morphism, and here filled with copies of this element we twisted. And again, the series is well defined because of the completeness of the filtration. And the last point is that if we have quasi-isomorphism between paired DGLAs, and if we twist with a Maurer-Gatan element pi, that the twisted morphism is then also an L-infinity quasi-isomorphism. Okay, so that's enough for the general things. So what we want to do now is to find such a diagram of L-infinity morphisms, right? So equivariant polyvector fields, equivariant polydifferential operators, and the DGLAs on a reduced manifold, and we want to connect them by L-infinity morphisms. And we start here downstairs. So this is just the conservative formality, or the globalized conservative formality. This is the easiest arrow in this diagram. So let's start with this. So first, there's the classical Hochschild-Costan-Rosenberg theorem that relates polyvector fields and polydifferential operators. So if you have some vector fields x0 to xp, then on the wedges of this, the map is just given by this kind of anti-symmetrization map. And the statement is that this map is a quasi-isomorphism of cosine complexes. And in cohomology, it's compatible with the brackets and also with the wedge and the cup product. So in cohomology, it's an isomorphism of Gerstenhaber algebras. Which is nice, but it's not enough for us because we want a map from Maurer-Gatan elements to Maurer-Gatan elements, which HKR does not satisfy. And this was solved by Kontsevich. So he proved that there exists an infinity quasi-isomorphism between Pulley vector fields and Pulley differential operators on RD, such that the first structure map is just HKR. So this directly implies that it's an infinity quasi-isomorphism just because HKR is a quasi-isomorphism of chain complexes. And well, this formality is pretty complicated, but you have some nice properties that you can use to globalize it. So for example, one property is that you can replace RD by its formal completion at the origin. And another property is that the formality is invariant under linear coordinate transformations. And there are some other properties, and so Dolgoshev used these properties to globalize the formality. So let me give you a very brief idea. So you start here with the Pulley vector fields with the usual structure, so zero differential and Schouten bracket. And you want to end up on the differential operators on M with Hochschild differential and gas number bracket. And what you do at first is you construct these Fedosov resolutions. So you consider these formal fiberwise Pulley vector fields and formal fiberwise Pulley differential operators. Then you consider like differential forms on M with ranges in them. So here you have a fiberwise Schouten bracket. Here you have fiberwise gas number bracket, and this is the fiberwise Hochschild differential. Then you can choose some torsion-free connection on the manifold M. And with this connection, you can define this Fedosov differential. And locally, it looks just like the Theorem differential here on the differential forms, plus the bracket with some element B, where this B depends on the connection. And using this Fedosov differential, you can define here Taylor expansions. And you can show that these, or Dolgoshev showed that these Taylor expansions are quasi-isomorphisms of DGLAs. So this is the first step. You build these Fedosov resolutions, and then you use that the conservative formality has these nice properties.
Could you explain how this B is related with this torsion-free connection?
Yes. So it's the Christoffel symbols of the connection plus some correction terms to make it flat, basically.
Can you write it down?
So you can start with, so another way to build this D is it's at first delta, which is just some shift. It kills a formal variable and gives the form degree. Then you can add here the Christoffel symbols of the connection. And this will not be flat, so the square, so d squared is not 0, but you can correct it by some term Dolgoshev calls it A to make it flat. And this A depends on the curvature. And then, so this connection here in local coordinates, it's the Theorem differential plus something depending on the Christoffel symbols and the coordinates. And then these three terms are the B. So the B depends on this operator which kills a formal variable and gives a form degree, the Christoffel symbols, and this correction term which depends on the curvature.
What is the degree of this correction term?
So the form degree is 1, but in formal variables it has at least degree 2. So this has no component in the formal variables, this also not. The Christoffel symbols have degree 1, and the correction term has degree at least 2. Is it okay? Well, so you have this Fedosov resolutions, and then you use the fact that the conservative formality also works at the formal completion. So it works also here. So this implies that you have here a fiberwise conservative formality, and then you want to make it compatible with this Fedosov differential. So you twist, so with this differential, so basically you twist the fiberwise conservative formality by this B. And this remains a quasi-isomorphism. And then in the last step, you use this general theorem that L infinity quasi-isomorphisms with quasi-inverses. So you can construct here the quasi-inverse, call it P, and then the globalized formality is just Taylor expansion. fiber-wise twisted conservationality, and then this projection downstairs here. And the first structure map is still just HKR. So this is the globalization procedure. And the globalization procedure is nice because it's compatible with group actions. So if you have on your manifold a group action such that there exists an invariant connection, then the globalized formality with respect to this connection is also equivalent. So for this reason, we will always assume that our group action on N is proper, because then there exists such an invariant connection and we have this equivalent infinity morphism. And well, another corollary is that the formality induces this bijection between the equivalence classes of formal Morgan elements. So this is the classification and existence of star products, right? So equivalence classes of star products are in one-to-one correspondence to equivalence classes of Poisson structures. And some side remark here. So the globalized formality depends on a connection, and it was shown by Burstein, Dolgoshev, and Waldman that this map star here does not depend on the choice of connection. And they computed like explicitly an equivalence transformation between the Morgan elements here. And Jonas and I lifted this statement. So we showed that if we take two different covariant derivatives, that then the globalized formalities are homotropic. And this implies in particular that this map is the same.
Sorry, in this star.
Yeah.
Does this def?
This is the equivalence classes of formal Morgan elements.
Okay.
So here
Your classes.
Yeah, the equivalence classes of
By
formal
passing to classes, you made this independent of the choice of the
without the equivalence classes, it's not
okay.
Exactly. Okay, so summarizing, we have this globalized formality, which is the first arrow in our diagram. So let's go to the second arrow, this above here, the equivalent formality. So we assume that we have this proper action with invariant connection, then we have the equivariant infinity morphism here. We can extend it to the DGLAs, where we just here tensorize with symmetric algebra of G star on the left, by just extending here the structure maps trivially. So the alphas are in symmetric algebra of G star, the x's are Pulley vector fields, and then the structure maps are just the usual structure maps on the Pulley vector fields, and the alphas are just multiplied together. And this is still equivariant, so we can restrict it to the invariants. And then we get this L-infinity morphism here between equivariant Pulley vector fields and equivariant Pulley differential operators. But now with here a different DGLA structure. So here is with zero curvature on both sides. So this is not what we want, because we want an L-infinity morphism between the curved DGLA, so with this lambda here. Because then the Morgan elements are just Poisson structure with momentum map, and then here in the formal case equivariant star products. So such an L-infinity morphism is called equivariant formality. Well, the name is a bit misleading, because usually under formality you would expect some L-infinity quasi-isomorphism. But here, in the case of curved DGLAs, there is no nice notion of quasi-isomorphisms, which is a bit bad. So this infinity morphism will, in the end, also only give like existence of equivariant subgroups. It will not classify them, because it does not induce this one-to-one correspondence on equivalence classes of Morgan elements.
So this lambda on the right hand side is the same.
Yeah,
as the one on the left hand side.
Yes. So here it's like this basis of G star, and then the fundamental vector field now seen as a differential operator. This is why right here this new derivative, and here it's just EI. So here it's just this. So it's the same. Just on one hand side it's a vector field, and right hand side it's a differential operator. Okay, so we have this L-infinity morphism between these DGLAs without the curvatures.
I'm confused by the use of the word. This term equivariant formality. If the left hand side, on the left hand side, the quasi-isomorph doesn't make sense because it's the curved version.
Yeah. So it's just
the formality means.
That's what I meant, that the name is a bit bad. So it's no formality, it's just an infinity morphism. But we call it like this. So we have this infinity morphism between the flat TGLA, so without the curvatures, and then this flat morphism is compatible with the curvatures if you have these compatibility conditions here. So the first condition is that the first structure maps curvature to curvature, and the higher structure maps should vanish if one argument is the curvature. So if this is satisfied, then we have this morphism here upstairs. And the second property here is clear because this F11 is just Hochschild-Rosenberg maps, so it maps vector field to vector field. And the left-hand side here is satisfied if we have this identity. So if the higher structure maps of the globalized formality vanish if one argument is a fundamental vector field. So we would like to understand if this property holds here. And
could you remind me why you call this lambda curvature?
Because we define it to be the curvature. So curvature means that the differential squared is the bracket with the curvature. So in a DGLA with curvature R, so you want D squared is the bracket with the curvature R, let's say. So this is satisfied here because the element lambda is central. So this is just so this will be just 0. So in fact, we have an honest DGLA structure, but artificially we include this curvature term. And the reason we include it is just that because the curved mode elements are nice.
But always you can change this R by any central element.
Yes.
So okay.
So it's just a matter how the Maurer-Cartan elements look like, because there it depends on this curvature. The Maurer-Cartan equation was like R plus d pi plus 1/2 pi with itself equals 0. So if you add here something central, then you have different Maurer-Cartan elements. Okay, so this equation downstairs is what we want to investigate. So fundamental vector fields inserted in the structure maps of the globalized formality. And at first we can look just on RD and the conservative formality. And there, one of the properties of the formality I mentioned, I didn't mention before, but the conservative formality has this property that for n greater than 1, so the higher structure maps, they vanish if you insert here a vector field that is constant or linear in the coordinates. So this means if we have some lead group action on RD such that the fundamental vector fields are constant or linear, then the conservative formality with fundamental vector field inserted here is just 0 by this reason, because the fundamental vector field is constant or linear. So in this case, we have this compatibility with the curvature. And so in this case, there exists this equivariant formality, which is no real formality. So this is the first example where we have such an infinity morphism between these curved DGLAs. And the next more general case where we could show the
could you repeat? Is this condition about U1 and consequence of some axiom, or is it postulate for obtaining some infinity morphism?
So this conservative formality is like built out of two parts. You have these graphs with their weights and the associated differential operators. And conservative just showed that for such terms, the weights vanish.
So this is irrelevant, because it is independent of equivariance.
Yes. So this holds each other.
Okay.
But we use it because.
And now you are switching on the G action and then.
And then, yes, and so I want to show this identity. Sorry, that my formality vanishes if I insert a fundamental vector field here. And I know conservative formality vanishes if I insert constant or linear vector field. So this means if my fundamental vector field is constant or linear, it vanishes trivially. So this is just this example. If I have a linear action, then the fundamental vector field is linear. So this vanishes here, and this is what we wanted. It's okay, or
Yeah.
okay. So this RD with linear action works, and the next case that works is a general manifold with a flat. So the flatness is the important thing here. Torsion-free connection and invariant. So in this case, this globalized similarity is also compatible with the curvature, and we have this morphism between the curved digits. So why is it the case? So the globalization procedure was like this: at first Taylor expansion, then twisted fiberwise similarity, and then this projection downstairs. And you can check that if the connection here is flat, then this B here, which was this B was like this D plus Christoffel symbols plus this A. So this here is constant in the formal coordinates. It doesn't contribute by the property from the last slide. This is linear. It also does not contribute. And this depends on the curvature. This will be 0 if our connection is flat. So this is also not there. So you don't have to twist the fiberwise formality. And then the expression that we want, so fundamental vector field in the globalized formality, is just this one. Taylor expansion of the fundamental vector field and of the rest of the arguments. Then the structural of the fiberwise conservative formality, and then just the one component of this projection. And then you can prove that the Taylor expansion of the fundamental vector field is only constant in linear terms. So this one will be 0 by the property of the conservative formality. And so we're also done. We have this compatibility.
So can I ask a question about this?
Go ahead.
So when I'm admits a flat torsion-free connection, I remember, I'm not sure I'm right, but I remember that this is the case of, is equivalent to say that M is a affine smooth manifold. So it has an atlas where coordinate changes are linear. So I don't know if this, you have a G invariant in addition. So I don't know if this is some kind of smooth manifold, maybe with a name. Do you know if affine smooth manifolds with a G invariant torsion-free connection, if they are something special? Or...
I don't know, sorry. No idea.
No problem, thanks.
And so could be this assumption, this position phrase that the action of G in some special coordinates is affine, by affine transformations.
Might be, I'm not sure.
So it's a very special case.
It's very special, yes. So for generals with manifolds, we didn't manage to show this compatibility. We just have that we have this identity here for the lowest 2 structure maps. And we would like to have it for all structure maps, right? And well, so for the lowest 2 orders, you can do it just by brute force computation. So you count the formal decrease and see that all terms vanish.
So, sorry, so in a sense, you are assuming that everything linearizes.
Yeah.
Everything is of order 1.
Yeah. So I have no examples for this. I don't know how special it is. Yeah.
Yeah.
I think it's pretty special.
Well, I mean, a simple example where you have a flat torsion-free connection is on a 2 torus or a sphere Cartesian product with a circle. But I don't know if it is a G invariant for some G. Probably is invariant for what one would expect, the symmetric group of the manifold. So if you're looking for explicit example, a sphere Cartesian product with a circle, that would be an explicit example of this kind of manifold.
Okay, thank you. Maybe we should look at it.
If I could add something to this comment. But then you can go to the universal covering of your space. I'm talking to Francesco. And then you will obtain the G invariant when G is the fundamental group of this flat manifold.
So, I mean, there is a whole theory, again, I'm not completely sure because I'm not an expert, but for these affine smooth manifolds, the existence of this special atlas is equivalent to saying that the universal covering has a developing map to affine space, to Rn for some n. So the universal covering has some special structure, is basically a subset or probably a subset of Rn, I don't know. I don't remember this developing map of what are the properties, but then maybe there is a G equivalent version of these developing maps. I don't know. Again, I'm not an expert, but there is a whole chapter of differential geometry about it is.
Okay, so point is just in general case, we know we have this property for the lowest structure maps, but not for the higher ones because they get too complicated to do brute force computations. But it somehow suggests that it should work. But well, this is work in progress. So the point is that we can use this L-infinity morphism to get this arrow upstairs here. But we have to slightly modify it because in our diagram, we have fixed here the reduced manifold. So we kind of want to consider here upstairs only Poisson structures with momentum maps that reduce to this same reduced manifold. So we kind of have to fix the momentum map. So let's assume that we have this map as we saw in this special flat setting. Then we can twist it. And then at first we fix some classical momentum maps such that the mass Weinstein reduction is this in red from our diagram. We can twist our morphism with minus J0. The twisted DGA structures look like this. So here we add just the bracket with J0 as differential. And where we have this twisted morphism, and this is indeed well defined by degree reason. So in this general proposition from before, I had this twist just in the case of complete descending filtrations, which we don't have here. But you can argue that by degree reasons, this is also well defined. And then you consider like formal power series, rescale the curvature, and this is then the structures we want to consider. So here the differentials with minus this minus this momentum. The point is now that in these DGLAs here, the Maurer elements will correspond on the left-hand side to formal Poisson structures with formal momentum maps deforming this J0 and the same on the right-hand side. So here you have ignorant subplots where the quantum momentum map deforms this J0. So these structures will all reduce to the same reduced manifold. So this same M right here.
Sorry, what do you mean by pi 0?
So this is just some classical Poisson structure with a classical momentum map, such that the mass Weinstein reduction is this M red that we want in our diagram.
So in previous formulas, pi could be more general.
Yes, it can be more general. I just need to fix some classical data that I end up here always on the same reduced manifold. Otherwise, if I get different manifolds here, it's a bit messy. Okay, so now these are the two quantization errors, and we can go now to the reduction part. So at first, some general stuff. So as I told you, we assume that our group action is proper on the manifold, and that we have this classical Poisson structure with classical momentum map that we fixed for the mass Weinstein reduction. And then there's this statement, again, due to Bordemann, Herbig, and Waldmann, that there exists a G invariant open neighborhood M nice of C in M, and an open neighborhood U nice of C in this product, and an ignorant diffeomorphism between the two. And well, on C times G star, the group action is just the product of the action on C and the coadjoint action. And this diffeomorphism maps the momentum map on M nice to just the projection to G star. So on C times G star, the momentum map is very easy. It's just the projection to the second vector. And we are just interested in the reduction. So for us, M nice is
essentially this proposition is a slice theorem.
Yeah. So it's just some tubular neighborhood, and because the action is proper, you can arrange it in such a way.
And what is C?
So C is our constraint surface. So we fix this classical Poisson structure with classical momentum map. And then C is the pre-image of 0 under this momentum map. This is from the master Weinstein reduction. And then M red is C mod G. So this is just to say that M looks locally like C times G star, and we can work with C times G star, which is much easier. So for example, the fundamental vector field on C times G star is just fundamental vector field on C, and the fundamental vector field of the coadjoint action, which is just minus the adjoint action if you want. So these are the structure constants of the algebra. And what's also nice is that C times G star is the dual of C times G, and this has the structure of an actually algebraic. So its dual has a linear Poisson structure. So this KKS structure, the first term is just the lead bracket G, and the second term is just the action on C in some sense.
By FKKIJ?
The structure yeah, so this is very simple Poisson structure on C times G star, such that this projection to G star is a momentum map for this package. So the easiest example of Poisson structure with momentum map here. And what's also another thing about this C times G star is that we can perform some kind of Taylor expansion in G star direction, which will simplify our computations. So taking here a smooth function, we can define this series. So we differentiate our function in G star direction and then restrict it to C, and tensorize with the elements which differentiate with. So we end up here in this symmetric algebra of G times the smooth functions in C and the completed product, because we have here infinitely many terms. And well, this Taylor expansion is compatible with the group action, and you can extend it to the vector fields, Pulley vector fields, and to these equivalent Pulley vector fields. So they looked like this, and if we use here this partial Taylor expansion, then we end up here. So the symmetric algebra of G star remains the same, and Pulley vector fields become like Pulley vector fields on C. These are the differentials in G star direction, and this is the function part in G star. And well, this Taylor expansion is compatible with the group action, is compatible with the Schouten bracket, and we just denote the image of this curvature lambda and of the momentum map again by lambda and J, and we have this morphism of curved digital A's here. And well, it was our aim to get from here to get from the left-hand side to the reduced manifold, and using this Taylor expansion, we can start instead now on the right-hand side. So we want to find a morphism from this Taylor expansion to the vector fields in the reduced manifold. And what we did at first is to look at this DGLA again, forgetting the curvature. So what is the cohomology of this DGLA? And there we have this proposition. So you can consider this space, which is just functions on G star times Pulley vector fields on C. The bracket is just the Schouten bracket on the second tensor factor, and you can include this in the Taylor expansion. And this inclusion becomes a quasi-isomorphism of DGLAs now. So the proof is pretty easy. So the Taylor expansion were these four terms here, and the momentum map on C times G star is just the projection to G star. So J in here is just EI tensor EI tensor 1. And so the bracket with J is just some kind of Cosmic differential. So it multiplies here with the basis element and inserts here the dual basis element. So we have directly the homotopy for this. That goes the other way around. So this homotopy multiplies here and inserts here. And then the graded commutator of the differential and the homotopy counts just the degrees of psi and alpha. So it counts just these two degrees. So in cohomology, you have just elements with no G star degrees. So this one.
Euler field with respect to the gradient.
Yes. Okay, so this is one part. Now we had on C times G star, we also had this Poisson, this KKS Poisson structure. And if you compute here the Lie bracket with this pi KKS, you get two terms. This one is the Chevalier-Eilenberg differential on the last three terms. And this del has this expression. So it's again Kosul type differential. You insert in one slot and multiply the other slot here. And the claim is that this del here on this cohomology from the last slide defines a DGLA structure. So I mean that it squares to zero is clear because this is symmetric, this is anti-symmetric. But you have to check that it's a derivation of the bracket, and this follows from the invariance. And then if we add on the Taylor expansion the KKS Poisson structure, and on the left-hand side this del, this remains a quasi-isomorphism of GS.
Sorry, I've noticed something. If you have this tensor product of symmetric power of G star and the exterior power of, so these are polynomial.
So this one?
Yeah. You could put them together, and this will be this will be polynomial differential forms on G. Okay. And then this causal differential becomes the usual Theorem differential of these polynomial differential forms. Polynomial differential forms.
Yes.
I don't know if this observation is important.
I don't know. This is still a bit confusing for me. You have so many G's, G stars, symmetric algebras, wedges, and why they appear.
So essentially, you have two types of differentials. One related to this Eilenberg-Chevalier, corresponding to this polyvector fields, and this polynomial Theorem with respect to G star.
Yes.
But it is not a double complex.
So this one,
Yeah.
so this is
a
double
double
complex.
concept with respect to this pair of these differentials, or something more complicated?
Something mixing between.
Mixed.
Yeah.
Okay.
Okay, and well, I call now, or we call now the left-hand side Cartan model for polyvector fields. And the reason is that you have this Cartan model for equivariant Theorem cohomology, which are just differential forms, tensored with symmetric algebra of G star and invariance. And differential is here than the Theorem differential plus this one. And well, this is kind of dual of this. So instead of differential forms, we have vector fields. Instead of symmetric algebra of G, we have H star, we have completed symmetric algebra of G. And instead of this one, where we insert the fundamental vector field and multiply here, we do it the other way around. We insert here and multiply the fundamental vector field. So it's kind of the dual of this Cartan model for the Theorem cohomology. And well, for this Cartan model for equivariant cohomology, you also have that if the action on C is proper and free, then the cohomology is indeed just the Theorem cohomology on the quotient. And we have again something similar here because the cohomology of this one will be just the vector fields on the quotient.
Sorry, what about this G? Isn't it G star? The definition of Cartan model.
No, here this is what remained in the cohomology. It was just functions on G star. So it's kind
Function from G star, yes.
Yeah. So it's kind of dual to this G star. That's all a bit confusing, right? We started with these equivariant polyvector fields, and they were like S G star tensor T poly of n invariance. So you could also call kind of this Cartan model. But well, we chose to call this Cartan model because it's kind of a dual version of this. I don't know.
Sorry, because I have a problem with this E upper I and E lower I.
here, or
Yeah. So if this is not G star, then I don't understand this combination.
so this E upper I can insert in G. So just dual pairing.
Okay, so E upper. Okay, so E lower I are related to G star this time or not?
No. So
Yeah.
G, these are like EI, V, EJ, V, I don't know, something. And then I can pair it with this one. Just a dual pair.
I'm asking about this appearance of E upper I on the right hand side
So this.
and E lower I.
So this is the fundamental vector field.
E upper I is a basic vector of
G star.
the G star.
So E upper I is the basis of G star, yes. And I can pair it with the G components here.
Okay, and you contract with
Yes.
this dual.
Just
functional-
this
Yeah.
natural pairing extended basis derivation. Okay, so we have this Cartan model here, and we can project now to the reduced manifold, and this projection will become a quasi-isomorphism of DGAs. So what is it? So at first we project like to symmetric degree 0 tensor Pulley vector fields. So what we have is just an invariant Pulley vector field on C, and invariant Pulley vector fields are projectable to the quotient, so we can really project to T Pulley of M red. And to show that this is a quasi-isomorphism, you have to choose a principal fiber connection, and then you can build some homotopy for this differential here. So
Sorry. So I would like to understand this. In the case of a free action, the equivariant version is equivalent to the version of the quotient.
Yes.
Whatever you understand about this version of something.
Yeah.
Okay. So this is something of this sort, result of this sort. But do you assume that this action is free?
Yes, it's proper and free.
Proper and free. Oh,
Yes.
okay, thank you. Proper about free.
Okay.
Sorry,
No, we need it.
Okay.
I want to stay in the setting of smooth manifolds.
There are no assumptions in this proposition.
Yeah.
I forgot what.
Okay.
What are standing assumptions?
Yeah, so the action is always proper on all of M and proper and free on C on the constraint settings. So summarizing, we have this Cartan model. We can project downstairs to reduce manifold, and we could include it in this Taylor expansion. And well, this inclusion was a quasi-isomorphism, so it admits here this quasi-inverse, and the same is true for the formal power series, where we can rescale here this KKS and this del by some h bar degree. So we have now an L-infinity morphism from the Taylor expansion with this DGA structure to the reduced manifold, and this we can use to get the reduction morphism from this diagram that we want. So we want to start with equivalent Pulley vector fields on M with this DGA structure, and we want to end up in reduced manifold. And now M is just a general manifold. Then we have with proper action. So we have this proposition that there exists this M nice, which is diffeomorphic to this U nice in C times G star. So we can restrict to M nice, then we go to U nice, then we perform Taylor expansion, and we end up here. Then we saw on the last slide that we have from the Taylor expansion this L-infinity projection to the reduced manifold. And now the only problem is that here we have this curvature and J is differential, and here we have the KKS minus J is differential, no curvature. So we have to make this compatible, and this is just twisting. So if we twist here by minus h bar by KKS, then then this will cancel in differential, and the remaining differential is just a bracket with J as we want. But we get some curvature, and this here is the formula for the curvature. So it's a differential of the element we twist with plus 1/2 the bracket of this element. So pi KKS is a Poisson bracket, so this vanishes, and what remains is just the bracket of the momentum map with the Poisson structure, and this is just really this curvature h bar lambda that we want. So we can compose these two arrows and we get our reduction morphism upstairs that we wanted. So this is the third arrow here in the diagram. And some remarks. So for this construction of this reduction morphism, we had this map P, which was, I can go back, this was here the quasi-inverse of this inclusion here. And for this, there's some nice formula. So some recursive formula, the first structure map is just the projection. And the higher structure maps are then recursively defined by the lower structure maps composed with the. So this is the Lie bracket extended to the symmetric algebra. And this is the homotopy extended to the symmetric algebra. So there's something called symmetric tensor trick that tells you how to extend homotopies to symmetric powers. And another thing is in the proof, we twisted this P by pi KKS, but you can check that you don't need to twist so that the structure maps remain unchanged here. And last point about this vector field reduction.
Sorry, so the method of proof is perturbation leg or something like this from model start?
Yes, okay, exactly. And in this case, it's particularly easy. So for the differential operators, it will be more complicated. So we have this reduction morphism, T-red, which induces in particular a map from Maurer-Cartan elements to Maurer-Cartan elements. So it maps here formal Poisson structure with formal momentum map to formal Poisson structure downstairs. But for Poisson structures, we also saw that we have this Marsden-Weinstein reduction, and there's a BRST-like reduction for the formal power series. And well, the statement is that our morphism coincides with these classical reduction procedures. So we did indeed manage to somehow lift this Marsden-Weinstein reduction to an infinity morphism. Okay, so that's it for the vector fields. Now for the Pulley differential operators, here it's similar, so we can do the same steps as for vector fields. We can again start for simplicity with C times G star as manifold and do this Taylor expansion. And this will look somehow like this, not exactly, it's some subspace in here. So we have differential operators in C. These are the differentials in G star direction, and these are the functions on G star. And this symmetric algebra of G star remains unchanged. So this is kind of this Taylor expanded equivalent Pulley vector fields. And well, for the Pulley vector fields, we started with Taylor expansion, no curvature, and just this differential given by the momentum map, and computed the cohomology. And this was then this Cartan model. So now we want to do something similar, but well, we have the Hochschild differential in addition, so it's a lot more complicated. And the first thing you can do is to extend this homotopy for the J to Pulley differential operators. So for Pulley vector fields, the bracket with J was this cosine type of differential, multiplying on one side and inserting on the other. And we had the homotopy, which did it just the other way around. And so this leads us to this definition. So on some homogeneous element here, our homotopy should insert something in the symmetric algebra of G star, and then multiply here with the corresponding differential. Now the cut product is no longer antisymmetric, so we have to choose the side on which we want to multiply here. And well, it turns out that the right-hand side is the better choice, and you get some sign because you have to move this differential along D. So this is kind of the homotopy for this J here. And then we need something for the Hochschild differential. And there's a paper by De Wilde and Lecomte where they construct a homotopy for the Hochschild differential on the smooth functions on RD. And we copied one function they used in their construction, this phi. So this is a map that takes a differential operator with A plus 1 slots and gives us something with just A slots by this formula. So you insert in one slot some basis element of G, some linear function on G star, and some slot on the right that's differentiated with respect to the same coordinate. And well, it's just some lengthy computation that these two maps do what you want. So if you take these two maps with some degree factor in front, so this counts the degree in the symmetric algebra of G star, and this counts the number of differentiations in G star direction. And well, you can compute that this is indeed homotopy for this deformation described here. So this is similar to this Cartan model for vector fields that we had, only that we use now differential operators instead of vector fields. Here you have like the Hochschild differential on the second factor extended to this product. You can include it in the Taylor expansion. You can project downstairs. And well, you have this compatibility. So this H is a homotopy for IP. If I include it and project downstairs, I get the identity. And the compositions of the homotopy with inclusion and projection are just 0. And well, we call this space here again D-card because it's kind of the Cartan model for differential operators if you want. Okay, so this is the first step. And then if you remember for the Pulley vector fields, we added then here this pi KKS as a differential on the Taylor expansion. So we want to do the same for the differential operators. So we need to understand what the analog of this pi KKS is.
So is H squared equal to 0?
No, this is the only thing missing here. Really. So because the cup product is now not anti-symmetric, so but all the other properties you want, you have just this one misses. Okay, so now we need to find the quantum analog of this KKS Poisson structure. And this is the product on the universal analog algebra. So I told you this C times G star has the structure of an action Lie algebroid, and for Lie algebroids there is a notion of universal analog algebras. And well, in our case, this action Lie algebroid is trivial. So this is just isomorphic to the smooth functions tensor the universal analog algebra of the Lie algebra. And by this H bar I mean that you consider this ideal, which is generated by psi tensor. So just you will scale the Lie bracket by H bar. So the idea about this. And okay, then you use pointer apical fit, so this universal in the branch bar is isomorphic to the symmetric algebra of G from a power series.
So the last isomorphism is a non-canonical isomorphism of vector spaces.
Yes. So I mean, you use this symmetrization that from SG to universal analog algebra. And with this, you can transfer the product on the universal analog algebra to this space. And this is kind of the quantum analog of the KKS Poisson structure. So it's the pointwise product and the symmetric product in order 0 of H bar plus some higher order deformations. And there are also some nice formulas for these higher orders. But what's important for us is that this product is invariant and that this is a quantum momentum. So this projection to G star is a quantum momentum map, which means that quantum action and classical action coincide.
So could you remind me how this n lower star affects this multiplication of SG, S of G?
It's the good star product. So on elements in just here, it's the good star product.
Okay.
So you take the symmetrization map to the universal analog algebra, multiply there, and go back.
Okay.
So it's just nested commutators, and each time you take a commutator, you get some H bar. Yes, that's the Lie brackets. Okay, so this is the quantum analog of the KKS Poisson structure. So we want to perturb our complex byte. So this was the vector field case. We had Taylor expansion, this Cartan model, here KKS, and here this induced differential. Now we want to do the same for Pulley differential operators. So we perturb the right-hand side by this H bar star. Then the new differential is the star product minus J. And now we use exactly homological perturbation lemma to get the deformed differential here and the deformed inclusion map here. Okay, so do I have till 45 or how much?
Yeah, we have 5 more minutes.
Okay, so then I skip a bit. So for Pulley vector fields, this was pretty easy because this was a quasi-isomorphism of DGLAs, and then we could compute the L infinity quasi-inverse. But here now we use the homological perturbation lemma, so we get here some deformed inclusion, which is no longer a DGLA quasi-isomorphism. So we can not invert it, and we have to use instead the homotopy transfer theorem. So let me just skip to this slide. So the homotopy transfer theorem says that you have such a homotopy retract, and such that one side is a DGLA or an infinity algebra, then you can transfer this structure to the other side. So you get here a transferred L infinity structure, and you get an L infinity morphism between them. And there are some formulas for these structures. So the transferred L infinity structure, the first component is just this perturbed differential. So this is the differential that we get out of the homological perturbation lemma. And the higher brackets downstairs, so you have this perturbed inclusion. So you go upstairs, take there the bracket, and then project downstairs. So these are the higher brackets. And similarly, you have for this projection downstairs some recursive formulas, including the homotopy, the brackets, and the lower structure maps. So the point is, we still want to get like to the Pulley differential operators on the reduced manifold. So we need to get from this side to the reduced manifold. And there you can compute at first that this transferred L infinity structure is in fact only a DGLA structure. So we have no higher brackets. And then you can check that this projection, which projects at first to symmetric degree 0, and then to reduced manifold, is a DGLA morphism. So then you can do the same as Pulley vector fields to obtain this global reduction morphism. So you start with the general manifold, you go to M nice, then U nice, and then to Taylor expansion. Then composing the arrows, the morphisms from the last slides, we get this morphism from the Taylor expansion to reduced manifold, but now with this differential. And then you just twist back by this quantum analog of KKS. The twisted structures are really the same what you want. Here nothing changes. You compose it and you're done. So I'm a bit fast now, but the idea is just it's the same as for vector fields. And yeah, the important part was before we used the homotopy transfer theorem and the perturbation lemma. So summarizing, we have now this morphism we have always, this also, and this we have for this special flat setting. And of course, we would like to know if this equivalent probability exists also in more general cases. But there we need some different strategy to show this. And well, finally, we would like to investigate if this diagram commutes. But before we do this, there's two other things we would like to show. So for the vector fields, I said that this reduction morphism on Maurer-Cartan elements generalizes Marsden-Weinstein reduction and this BRST reduction of formal Poisson structures. So what about here? So is this on Maurer-Cartan elements just this BRST reduction by Borderman, Helbig, Waldman, or what is it? So we would like to compare it. And then the way we constructed this reduction morphisms, we use this tubular neighborhood that M looks locally like C times G star. And there, if we choose like different tubular neighborhoods, then this should lead to homotopic reduction morphisms. So this also remains to be done. Okay, well, here's some references. So all the stuff is in my PhD thesis. The Pulley vector field reduction is accepted for publication. And this homotopic global formalities is a preprint. And well, the differential operators we're just writing down. And here are some other references that I cited. And then I thank you for your attention.
Thank you so much. I think you have a spelling mistake here. I think that these two letters are interchanged.
Ah, might be yes. Sorry.
And we know it because it's a Polish surname, and Bursztyn means ember in Polish. This is why we studied it. Okay, so let's begin with questions. How about some expert like Richard? Richard, any comments, questions? We don't hear you. You are.
Hey, no, we've been talking about it all the time, so no comments at the moment.
Okay, good. Anybody else? Any further questions? We had some questions during the talk.
Just sorry for barging in. May I ask a question?
Of course, yes, but please show it.
I'm sorry, just here I am.
Yes.
Hello.
Hello, Rosa.
Hello. Just as far as I can understand, you have some equivariant quantization in case of proper action. So I wonder whether this can be applied to some integrable system where you consider the action of bivector fields which commute with each other in Hamiltonian vector fields. Is there a kind of example you can apply this to?
I'm sorry, I don't know.
I see. I'm sorry, just because this is one example which is actually which is very intriguing. Okay, thank you.
Sorry, Gosha, if I could comment. If you have this invariant torus related to this action of the torus, then it's a part of this general theorem.
Yeah, sure.
So if you think about orbits which are not compact, then maybe there is some difference. But
well, the problem is that even if all your orbits are tori, this tori can have different radii, so to say. So in general, this action can be pretty complicated. You see,
yes.
It's only completely resonant case where you have proper action, I believe. I'm not sure about this. Maybe there are some other cases, but definitely you need some commeasurable length of the story. Otherwise, the action can be pretty nasty.
Okay, anybody else? Maybe co-author. I see Jonas here. Any comments, complaints, suggestions? Since everybody is happy. Adam, you didn't ask any question today.
Yes, but I will have to watch this this lecture once more. There are a lot of stuff which I don't know, so I don't have any good question.
Okay, so if there are no other questions,
I would have one.
so go ahead.
If you allow me to ask a stupid question.
Good question.
My question is like this. If you think about changing the curvature by adding some lambda, which is central, it is like considering, let's say, some vector bundle with some connection up to twisting by a line bundle. Then the curvature of this line bundle then is the central element. Can I have some mental picture about this lambda in the sense of some projective equivalence of some curved infinity algebras here?
I don't know. Richard, do you know? You invented
What
this
is this
stuff.
lambda?
No.
Can this lambda be?
No, it's no. So
formal
no.
lambda.
No, it's part of a structure, right? So it's just, of course, this curvature is not defined uniquely in this sense, right? So, or rather, we can do different curvatures for the same D, right? As you said, but that's more because you work with two groupoids. So with the deformations thing, it's really a two groupoid, and the curvature part is the well -1 component of this two groupoid, which is just extra part of the data, which is there.
Yeah, but I expect in this situation some kind of a formal tautological line bundle, which is a part of the structure.
No, it's not tautological. It's more like you have a line bundle, you have a connection, then you can change a connection. Well, the curve, I'm not sure how to explain it, but it's nothing tautological. It's an extra data, which is there. It's more like you have different equivalent representations of something, but they're equivalent, but they're not the same. So you implement automorphism of compact operators, right? So it's conjugation by a unitary. This unitary is not unique, it's up to a constant. It does not show until you start gluing things together, right? So this curvature shows, even the scalar part shows up. So locally you can get rid of it, right? As you said.
Okay, so is this a line bundle related to some germ condition?
It's kind of germ condition. It's just kind of germ that's floating around.
Thank you very much.
Actually, that's where it shows up first, right? When you do the formation of, say, complex manifolds. So in general, you get some kind of germ deformation.
Okay.
And precisely this bit of curvature shows up. The scalar part of the curvature shows up.
Very good question. Yes. Thank you very much.
Excellent. Okay. Anybody else? Well, in this case, let's thank Andreas again.
Thank you so much.
Now let's stop recording, Andreas.